Okay. So last time we saw if we have two dielectrics, say one is epsilon R1, the other one is epsilon R2, then suppose this is E tangential 1 and at this point, right? And say at some other point we have E tangential 2, right? We concluded last time that the tangential component is not going to change. Even if there's a tangential component coming from dielectric 1, that will simply go through into the dielectric 2 as it is, right? So it's not going to change the tangential component at the boundary. So dielectric boundary, if it's a perfect dielectric boundary, it will not affect the tangential component of the electric field. Okay, so that was a last conclusion. What happens to the normal component? The normal component, say we have
तो वो
this
चेंज नहीं
not.
होता.
Yes, exactly. Said this is D normal 1
डी
and
नॉट.
said this one is D normal 2. Or even if we say some normal components coming from this medium, say D normal 1 and let we call this as D normal 2, the the normal component will only bring if there are free charges in the dielectric. If say there are free charges in the dielectric, the normal component will only bring free charges to the boundary. Okay, it will only bring free charge. Let I change the direction of the electric field. Let I say the electric field is coming from here and entering into this medium, right? So this electron will move to the surface. So the normal component will only bring free charges to the surface if there are free charges. If there are no free charges, then the D normal 1 will be equals to D normal 2, right? Uh, if there are free charges, then it will be charges divided by the area upon which the electric field is falling, right? It's the area of the surface upon which the electric field is falling, right? So it will bring charges to the surface, right? If the charges are say 0, there are no free charges, then the D normal 1 will also be continuous. Okay, it will also be continuous, will happen nothing to it, right? But remember, for all real mediums, there will be free charges or free or ions or the charged particles. For example, the best dielectric known to us as a material, not as a free space. Free space, see, there's nothing over there, and no mass is there, and no positive charge is there, no negative charge is there, and even not an atom is there, not a neutral particle is there. Okay, so that's the kind of thing which has no free charges. So you can say that epsilon r is one for the free space. Uh, though it's not the dielectric, but it's the perfect kind of, the behavior is like a perfect dielectric. The free space, it's not a dielectric because it's not a material. Okay, but the best other dielectric known to us and actually is made is silicon dioxide. Uh, from which we use this in fiber optics, right? And through special process, this silicon dioxide is refined, right? Thereby removing from the silicon dioxide from the fiber, there may be the copper contents in it. There may be some iron, Fe2 plus ions, or there may be some Fe3 plus ion. There may be some water molecule, H2O. But since these fibers are refined at a temperature of 1400 degrees centigrade, so what happens? These water molecule loses one of the hydrogen and may transform into hydroxyl ions, thereby releasing one of the hydrogen atom. Okay, so even this best fiber material whose epsilon r is nearly in the range of 1.46, right? Is a very refined dielectric, very pure dielectric, but still have some free charges over there in it. A very good dielectric, almost a perfect dielectric, but there are still some free charges are there or ions are there, which will basically reduce down the normal component of the electric field whenever it hits. Okay, because what happens when the electric field suppose in the electric field suppose hits, say, from this direction, just I'm creating a case of the normal component, this hydroxyl ion will come down to the surface. Okay, so thereby reducing the electric field which is leaving the fiber. Okay, this is just an example. Okay, typically inside the fiber, the electric field has this direction, like it goes through total internal reflections. The light the light goes through the fiber through total internal reflections, so that's a typical case, because light is electromagnetic wave. But this red electric field, I was just trying to create the case where we were studying the boundary conditions. Then we saw last time the definition of the capacitor. And we said if you have two metals, they're separated from one another through a dielectric, we end up on a capacitor. And then we saw the capacitance here was C equals to epsilon naught. A is the area of the plate divided by D. So that was the capacitance of this structure. If the two plates are separated by air, suppose, which has very, very near epsilon r, very close to 1, if the two plates are separated by air. Okay, I guess we have two zeros here. Yeah. Okay, and then we saw if we fill the same structure with a green dielectric, okay, then the capacitance is still epsilon naught A divided by D, but now the green material has epsilon R also, so we have epsilon R also. So the capacitance of the structure is little bit higher now, because epsilon R is always greater than 1. Okay, so the higher the epsilon R, the more the capacitance you will get of the structure, out of the structure. So typically there are many dielectrics which you can use here. For example, barium titanate. Okay, for example, Teflon you can use. Okay, so there are many dielectrics you have which you can use here as the dielectric material. So the higher the epsilon r, the more the capacitance you will end up on. But the problem is the higher epsilon r also will weak this structure, because then if the epsilon r is very high, there's a probability that this charge comes down here and the capacitor might get short circuit for certain voltage, for certain high enough voltage. Okay, because always remember there will be some voltage VA here and there will be some voltage VB here, and VA minus VB, VB minus VA is VAB, right? VAB, and see the separation, VAB divided by D, you will get the electric field. If this electric field gets enough value, the breakdown may occur. Okay, so those kind of things are already known to us. So here we saw the definition of the capacitance. The capacitance is basically charge divided by the voltage. So capacitance of a structure is a function of the geometry of the structure and the dielectric constant. Then we saw parallel plate capacitor. And what if we fill the two parallel plates with two different dielectrics, say epsilon R1 and epsilon R2? What if we fill the structure with the green dielectric and the white dielectric? Then we saw that this structure is like we have two capacitors. It's very similar, like we have two capacitors in series. we equivalently calculated this structure through some mathematics last time, and we showed that this structure is like we have another conductor. It's like we have another conductor, this one, at the boundary, at the boundary, at this boundary, at this boundary between the white dielectric and the green dielectric. So it's like we have an imaginary conductor at the interface between white dielectric and the green dielectric. Physically, this conductor does not exist, but the structure behaves in that way. So an equivalent diagram is like this, like we have the, if we fill two metallic plates with two different dielectrics, it's like we have two different capacitors connected in series together. Okay, so then the total capacitance of the structure will be the inverse of first capacitance plus inverse of second capacitance whole inverse, and that this we saw in our previous lecture. Okay, so and equivalently we end up on this structure. It's like we have two different, then we saw very simple example, just go through it, probably very simple example. If you want me to solve this, I can do that very quickly. Aluminum foil of 100 square area. So we have the conductor is aluminium. American calls this as aluminum. Uh, we have conductor is aluminum, and the area of this is 100 centimeter squares, is placed on both sides of the paper of thickness of 0.0. So we have this aluminum conductor. Okay, we have another aluminum conductor. The area of this is 100 centimeter square. The separation between the two, the two conductors are separated by paper whose thickness is 0.03 millimeter, right? So we have paper here. Okay, as a dielectric, the dielectric is paper. Okay, if the dielectric constant of the paper epsilon r of the paper is 3, and its dielectric breakdown strength maximum value is, so the dielectric EBD, electric breakdown strength of this paper, of the paper, okay, is 2 into 10 to the power 5 volts per centimeter. Okay, this is the electric breakdown of the paper. If the electric field is raised from this value, what will happen? Say we have all negative charge on this plate and all positive charge on this plate. Okay, if the electric value, if the electric field value, if this electric field goes beyond, goes little beyond than this 2 into 10 to power 5 volts per centimeter, what will happen? This electron will jump to the other plate and spark will occur. And we say that a breakdown has occurred, the capacitor has been short circuited. Okay, so you need to avoid the electric breakdown. Remember, of course, you have to. Okay, so find the capacitance. You need to calculate the C, the capacitance of the capacitor, and the maximum voltage that can be applied across the capacitor. And V max we need to find so that we avoid the breakdown, right? Okay, so EBD is V max divided by D. So V max is EBD multiplied by D. Now you can calculate. EBD is known to you. D is known to you. D is 0. So this is 2 into 10 to the power 5 volts per centimeter multiplied by D. D is how much? This equals to 0.003 centimeters. So everything you are calculating in centimeter. 0.0003 centimeters. Okay. Okay. So from here you can calculate the Vmax. Okay. So find the capacitance of the capacitor. So capacitance of the capacitor is how much? Now how much is the capacitance? Anyone who can quickly solve this? Epsilon naught, epsilon r, a by d. So see the capacitance you can calculate. Epsilon naught is a constant, epsilon r is 3, a is given 100 square centimeter, d is also given to you. Okay. But this voltage, you need to not go beyond this voltage because then the breakdown will occur. Any question here? Any question? Okay, let me introduce here a little concept, okay, which basically happens to every capacitor. Suppose, okay, aluminum is a little bit gray. So let this is aluminum plate, okay. This is aluminum conductor, okay. Let we have another aluminum conductor, right? This is let we say this is another example, okay. Okay, so we have two aluminum conductors placed together, okay, and say there's between the two aluminiums we have suppose this dielectric, okay, we have this dielectric. Can be barium titanate, can be Teflon, can be any, can be a plastic sort of material, can be anything, right? So let we have a dielectric epsilon R1 here, okay, between two aluminum plates, which is there, right? And say this thickness, this one is say 0.5 mm, okay, just for example, just for example. This is 0.5 mm. The separation is between the two is 0.5 mm, right? So this one is a conductor, and the conductor is aluminum. This one is also a conductor, and the conductor is aluminum, right? So what's the capacitance? Capacitance is how much? What's the capacitance? Capacitance is,
So epsilon or A by D.
yeah, it's A divided by D. And of course, this plate will have some area. Okay, this will have some area A, right? Okay, so this is how you calculate the capacity. So it's so easy. But there's a problem with all metals, that they gets oxidized. Okay, so all metals are easily oxidized. ओके, जैसे लोहा है ना, आयरन, तो आयरन 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 को जब Fe2O3, राइट, Fe2O3 is iron oxide, okay, iron oxide, right? So basically what happens when you have a metal, it makes a reaction with oxygen in the presence of water molecules, and you know, there are plenty of water molecules in our atmosphere. So metal will react with oxygen in the presence of water molecules, to make a metal oxide. Okay, copper will have a copper oxide. आपने अगर कोई कॉपर की तार देखी हो जो शील्डेड ना हो, तो वो थोड़ी सी देर के बाद इन्वायरमेंट में थोड़ी सी ब्लैकिश हो जाती है। उसको आप उंगली से जब रब करते हो तो आपके उंगली पे ब्लैक सा पाउडर आ जाता है, हल्का हल्का नजर ना आने वाला, तो हल्का हल्का लाइक एक कलर सा आपको फील होता है, मास फील नहीं होता, बट दैट ब्लैकनेस, दैट ब्लैकिश मटेरियल इज बेसिकली कॉपर ऑक्साइड। ओके, जो उसके ऊपर कॉपर के ऊपर थोड़ा सा ऑक्सीजन की वजह से तो लोहे लोहे को अगर आप बाहर इन्वायरमेंट में रखें उसको जंग लग जाता है, दैट्स द आयरन ऑक्साइड। तो अब लोहा जो है, लोहे को जंग लगता जाता है, जंग लगता जाता है, वो असल और ऑक्सीजन वाटर की मॉलिक्यूल की प्रेजेंस में उसके साथ रिएक्शन करता जाता है और आयरन ऑक्साइड जंग लगता जाता है, राइट। और वो पेनिट्रेट होता जाता है, होता जाता है, और आयरन खत्म होता जाता है। बट द गुड थिंग अबाउट कॉपर और एल्यूमिनियम दोनों की अच्छी खूबी ये है कि जब इनके कॉपर ऑक्साइड एल्यूमिनियम ऑक्साइड बन जाते हैं तो वे फिर फर्दर पेनिट्रेशन ऑफ ऑक्सीजन को रोक देती है। तो वो जो कॉपर ऑक्साइड की जो लेयर है वो थिकर नहीं होती जाती वक्त के साथ, जैसे आयरन में थिक एंड थिक एंड थिक होती जाती है, कॉपर के केस में खास लेवल के बाद रुक जाती है। तो उसके फर्दर फिर पेनिट्रेशन ऑक्सीजन की होती नहीं है। सेम गोज फॉर एल्यूमिनियम, लेकिन एल्यूमिनियम में फिर भी थोड़ा कॉपर के मुकाबले में ज्यादा ऑक्साइड की लेयर बनती है, राइट। सो मीनिंग व्हाट वी मीन टू से कि when you have uh, when you have uh, this kind of situation जिसमें एल्यूमिनियम एयर में पड़ा हो, या इवन अगर आपने उसकी केसिंग भी की हो, इट्स वेरी डिफिकल्ट टू स्टॉप वाटर molecules from penetrating that casing. So they will penetrate, and if that happens, then aluminium की ऑक्सीडेशन होती है। सो जब एल्यूमिनियम की ऑक्सीडेशन होगी, रिमेंबर हमारे पास अभी भी वो जो डाइलेक्ट्रिक है वो पड़ा हुआ है, ठीक है। दोनों एल्यूमिनियम प्लेट्स के दरमियान डाइलेक्ट्रिक हमारा पड़ा हुआ है, ओके ओके। दिस वन इज आफ्टर few years, okay, after few years. So this is still aluminium, say this one is still aluminium, this is still aluminium, and this orange one is are still the same dielectric, can be anything, okay, can be anything. So once oxidation occurs, what happens, nothing will happen to the oxide layer, but it's the aluminium which will change its structure. So the aluminium layer will be pushed a little bit upward, okay, थोड़ा सा फूल जाएगा कैपेसिटर, हल्का सा, प्रॉबेबली आपको नजर ही ना आए, okay. तो this aluminum plate will again be pushed little bit downward because of the oxidation which is happening. And let me show the oxide, and see this kind of oxide layer is formed around the aluminum, around the metal, okay. Similarly on the downward side, okay okay, it's the oxidation which is here, that's a problem area, because really the oxidation here is of no interest for me, but it's this region where the oxidation layer between the dielectric and the aluminum, this oxidation layer, it will have some thickness, say like uh, like 0.2 micrometer. It's such a thin layer, or 0.1 micrometer. It's such a thin layer, very, very thin layer that will appear. Okay. And similarly here also, we have the oxide, the aluminum oxide. This red layer is, the red layer is, the red layer is aluminum. I don't know the chemical formula of this, that I need to check, but it say it's aluminum oxide, okay. This one is also aluminum oxide. Really, the aluminum oxide is also here, but I'm really not interested in that. Aluminum oxide is the layer which is I'm interested is in this region. And this aluminum oxide has epsilon R nearly 12. Okay, this aluminum oxide has epsilon R nearly, and this aluminum oxide is behaving like your third dielectric, second and third dielectric. So now we have a second dielectric here, epsilon R2, and a third dielectric here, epsilon R3. This is nearly 12. This is nearly 12. So now how many capacitors do we have in the same structure? Now we have C2 here, and because of the original dielectric, we have C1 here, and now we have C3 also here. And see, and all the three capacitors, they look like in series. Okay, so 1 over C total will be equals to 1 over C1 plus 1 over C2 plus 1 over C3. You can calculate that. That will be different than the original capacitance. So every capacitor is going to lose its capacitance over the years because of the oxidation of its metal plate. Okay? समझ आ रही है बात की? And you can calculate. You can really calculate. See, this was the C1. Here is C1. And there are C2 and C3. C2 and C3, they are same. Okay, so C2 is equal to epsilon naught, epsilon R 2, A still the same, and D2. D2 is how much? D2 is 0.1
1 micrometer.
micrometer. Similarly, we have C3, which is nearly same as C2, which equals to epsilon naught, epsilon R3. Epsilon R3 is basically epsilon R2. The two are same. This is because they both are aluminum oxides, and A is still the same, and D3. So D3 is nearly again 0.1 micrometer. Okay, so you calculate these three. Okay, बात ये समझ आ रही है? So जब आप
Yes, sir, it's clear.
for example, you are working for a capacitor manufacturer and you are designing this capacitor for a very serious application like say a computer. Uh, so you need to build a complete graph of this capacitor. Okay, so you say the capacitor which is being used on day one has capacitance C1, and after say 4 or 5 years, it will have the capacitance, it will have a change capacitance C total after some years. Okay, so how much change occurred in the capacitance? C1 minus C total is the change in the capacitance. So this kind of information you need to put on the specification sheet or on the manual of the capacitor on the specification. So see, a del C capacitor change has occurred in C1. So how much percent change will occur? So this will give you percent change in capacitance. Okay, after say 3 years, 4 years. So you need to build such graphs, basically simulate them to show the client. See, since you are working for a manufacturer, so your company is a vendor, so they will provide that capacitors data sheet with the, and will tell everything like how much capacitance on the day one, how much you will predict on day five, on year five, how much change will occur, percentage values, and all these tolerance values you put on the graph. Okay, and it happens, it affects the system performance, of course, because look, the capacitance will always bring the rise time for any circuit. Okay, the rise time is the rise in the voltage value. Because look, when you apply voltage to a certain device, the voltage will not suddenly rise to the maximum value. It will take a little time to rise to its maximum value. So the time taken by the voltage to rise to 63%, sometimes 66%, some other people quote like 63% of its maximum value is called as rise time. And that depends on capacitance. So if the capacitance value changes over the time, say, or in 4 years or 5 years, its rise time will change and your circuit will not perform in that way, especially if it's controlling some clocks. Okay, if it's taking some decision on the clocks, so now your clock's duration will be disturbed because of the change in the capacitance, because of change in the rise time, right? So these kind of things will affect your system and your system will not perform like it was doing in day one, on day one. Okay, any question here? Oh, okay. And any question by the way?
No, sir, no question. Clear, hai,
Oh,
sir.
okay, okay. Last time we also saw the this kind of arrangement for the capacitor. What if we have capacitors lying in this way? And we concluded that we end up again on two capacitance, but this time the capacitance, the two capacitors look like they're in parallel. Okay, why? Because this yellow capacitor is between VA and VB. This green capacitor is between VA and VB, the same voltage. So the green and the yellow capacitor, they both are in the same, between the same voltages, between the same points. So they look like in parallel. Say this is your VA line, say this is your VB line, this is your green capacitor, and here is your yellow capacitor. So it looks like the two capacitors are in parallel, and we have these equations for the parallel capacitors. You can check on that. Now coming back to the example of the coaxial cable. This example for us is very important and we'll be working on this for our rest of the course also. Uh, we know that the coaxial cable have an inner conductor, this pink one, and then we have this dielectric region. This is the dielectric region. Okay, this is epsilon r, this is the dielectric region, and then we have the outer conductor, which is the green one. Okay, so this pink is the inner conductor, the green is outer conductor, and we have the dielectric. Okay, so so every coaxial cable have a capacitance. Okay, so a coaxial cable have a capacitance. Okay, and again that capacitance you can easily calculate. The inner conductor has how much charge on the surface of the inner conductor? It's the rho L, the length of the conductor, divided by 2 pi a, the circumference of the conductor. Okay, uh, this circumference. Okay, if I talk about this circumference, how much this circumference is? How much is this circumference?